Very nice to be here and to be back again in Chennai. It's a very nice place. And I would like to thank the organizers for the invitation to this school. So I'm happy to deliver a couple of lectures on quantum chromodynamics to you. So what I thought we'd be doing over the next 4 days, every day at 10 o'clock in the morning, I would start off with a brief introduction to QCD. And since it's Monday morning, very early, I keep it basic. So I see a lot of experts in the audience on QCD, but I think we're going to start off slowly. And then I would like to move on to topics I call this QCD at work, and just introduce you to a couple of key concepts in QCD that you should know if you want to apply QCD to predict cross-sections at hadron colliders, like the Large Hadron Collider at CERN. So these topics are infrared safety, then factorization and evolution, and finally, last lecture I'll spend on discussing a little bit the non-perturbative part that we also need if we want to make cross-section computations at the LHC, namely the structure of the proton. So this is the rough outline. If you have questions or if anything is unclear, then please don't hesitate to ask me. So it's basically up to you to determine the pace, and then we'll see how far we get. Alright, so QCD, it's a fundamental force in nature. It's described by quantum fields which have an internal gauge symmetry. So there is this color SU3, non-abelian gauge theory, meaning we have quarks that come with 3 types of colors. So in total we have 6 quarks, their spin 1/2, each fermion, so we have up, down, strange charm, bottom and top. And they interact with gauge bosons, those are the gluons. And since they carry color charge, we have in total 8 spin 1 gluons which carry 8 different color combinations that you can make out of 3 colors, red, green and blue, for instance. Yeah? And then the interactions are described via Feynman diagrams. And so if we want to visualize this as color interactions, then we have a quark here, a green quark interacting with a gluon, which carries the combination green and red, and then out comes a red quark. Or we have in QCD we also have interactions between 3 gluons or 4 gluons, and that would look like this. Here, for instance, a green and blue gluon interacts with a green and red, and out comes a blue and red gluon, things like that. So this is how you can understand the color interaction, and this is what really distinguishes QCD from, say, its simpler cousin quantum electrodynamics. In theoretical physics, we like to start from a Lagrangian. So the classical part of the QCD Lagrangian is given by the field strength F mu F minus, which carries color indices here, and then you have the well-known Dirac action, which describes the kinetic and the interaction part of the quarks here. So psi bar and psi, these are the quark fields, and the fundamental representation of the SU3 gauge group. We have here a covariant derivative. This is the normal derivative d mu, the partial derivative, and then we couple the quarks to the gluons, like you do it in QED when you couple electrons to the photons. But since we have a non-abelian gauge theory, then the gluons also are accompanied by generators of the SU3 in the fundamental representation. So these are 3 by 3 matrices, 8 types of them. And we have the field strength. This also carries color charges. A runs from 1 to 8 in the adjoint representation, and you can describe the field strength in terms of partial derivatives acting on the gluons, d mu a nu and d mu a mu, and then the gluon self interaction. This is then the third term here, which is different. You don't have it in QED, in quantum electrodynamics. This comes with structure constants in the adjoint representation, FABC, and they couple two gluons together, A mu and A nu, and you have 1 power of the gauge coupling here. And then you square this, and you see that you basically get a kinetic term here for the gluons, and you get triple and quartic interactions of the gluons. Yeah? You can also write, like in QED, you can also express the field strength through commutator of two covariant derivatives in the adjoint representation. That basically gives you this expression here. So this is what we have, and with that we can basically describe all phenomena that we see at the Large Hadron Collider, but we have to do a bit of work. Huh? And what I would like to point out first of all is that we have a couple of formal parameters here in the theory, which are the quark masses here. So in the Dirac-Lagrangian here we have a mass parameter for the quarks. So up and down we can formally associate some mass, but typically we consider them to be massless. But then things like charm, bottom or top quarks, they certainly have a mass which is non-negligible. So we like to keep it here. But those parameters are formal parameters in the theory, like the strong coupling. So GS, the power of the strong coupling, we can square it divided by 4 pi, and then we come up with alpha S. So this is typically denoted as the strong coupling, and you should basically think of it as a formal parameter. And unless I give you a prescription of how to extract it, you cannot make sense of it in the first place. So what are the set of rules that we need to do when we want to compute, do computations with the theory? So first of all we have to quantize. And that proceeds in 2 steps. We have to do gauge fixing. Yeah, so there are gauge degrees of freedom, of course, in here. We have to fix this. And we can do this in a covariant gauge. For instance, by adding a gauge fixing term to the Lagrangian, which we can take as d mu a mu squared. And we can multiply it in order to keep track of the gauge fixing. By convention, we multiply it with a factor 1 over 2 lambda. And if we set lambda equal 1, then we are in Feynman gauge. So this is the part which we can add to the classical Lagrangian here. And then, of course, once we've done the gauge fixing and we continue with quantization of the theory, then we introduce so-called ghost fields. I denote them here as eta. So they come in with a d mu eta. And then this is a simple derivative acting on eta dagger, and then a covariant derivative acting on eta. These are in the adjoint representation, like the gluons, and their role is to remove the unphysical degrees of freedoms for the gauge field, so that in the end, when we do computations, we make sure we just have physical degrees of freedom for our interacting bosons. Yeah. So these are the 2 terms that we add to the Lagrangian, and this is very general for any SUN gauge theory. So those steps you're doing for any SUN gauge theory. It means when we are done with this step, we have our classical Lagrangian, we have the gauge fixed term, and we have the ghost term. So this is all we need to start with, and this is also all we need to derive the computational rules if we want to study this theory in perturbation theory. Right, and then what we do is we actually take this sum of the Lagrangians and we decompose it into an action part which we call the free action and an inacting part. So the free action here, that contains just every term in our Lagrangian which is bilinear in the fields. So for instance, a bilinear in the field for the quarks is like the psi bar and then the partial derivative acting on the psi, or the mass sandwiched between psi bar psi. Yeah? So this is the free part, and then the other part we put into the interaction part of the action. This would be, for instance, if we stick with the Dirac-Lagrangian here, this would be the psi bar multiplying here the coupling to the gluon psi. So this would be the interaction part here. So there we have 3 fields, 3 quantum fields coupled together, versus the free action part where we only have bilinear terms in those fields. So this is the way we can decompose the things, and then from the bilinear terms we can derive the propagators. This is basically giving us the giving us the dynamics of the theory. So for instance, if we want to derive the fermion propagator in QCD, we pick the bilinear parts in the fields. So this is everything we have there, psi bar d slash minus mq acting on psi. And this is an expression in position space, and we typically like to do computations in momentum space. So that means we do a Fourier transform, but a Fourier transform is a very simple operation. It basically just means we have a substitution of this partial derivative in position space by minus I pi times the p mu, the momentum which we associate here to the quark fields in momentum space. And with that substitution, so we replace here the d slash by minus I pi p slash. With that substitution, we directly can read of the inverse propagator of the quark fields. So I denote this by gamma psi bar psi. So this is then minus I and a delta in the color indices, and then we have a p slash minus mq. And it's the same like you have in quantum electrodynamics, except for the Kronecker delta in the colors here. And we can do a quick check. We can basically multiply the inverse propagator with the quark propagator here. So we take the product of the gamma times the delta, and then we see that we get out unity. So this is actually then the expression for the quark propagator in QCD, plus I times delta ij 1 over p slash minus mq. And then in cases it is important to keep causality in your computations, so to make sure whether you're in forward or backward light cone with your event, and this is why we put here this prescription of plus I0 sometimes to denote or to distinguish the propagators in the subsequent steps in time. What is there? This is an I, yeah.
In the action?
So it depends on. So typically you have an imaginary action when you work in Minkowski space, and then you can do a Wick rotation, and you end up with e to the minus the action in Euclidean space. Yeah.
So you're doing a Euclidean computation?
Sorry?
You're working in Euclidean?
No, this is Minkowski. Yeah.
Why does Minkowski have an I?
He absorbed the I from the to the power minus IS.
Then that's not the action.
So I didn't write you down the functional integral where I integrate over all the fields, and then basically in the Euclidean region you have so it depends on how you define the functional integral. So
okay, so you're putting the e to the is that I explicitly here. So that's not the action. It's I times the action.
If you're working in Minkowski space, then you have an exponential of I times the action, and if you work in Euclidean space, it basically falls off e to the minus, so that functional integration makes sense. So I skipped that part. So if you have questions on that, we can discuss it further on.
Regarding age fixing procedure, you ever use the large case transformation calculation? Always the Faddeev-Popov method is always suitable in whatever calculation is typically done.
Right. So this is so for all what we're doing here, we basically use gauge transformations in the vicinity of unity. Yeah? We can of course have large gauge transformations, which would then require us to define basically a winding number for Young-Mills theory in general. And we could do this for, say, topologically distinct configurations. But for all we're doing here, we're doing perturbative QCD in the trivial vacuum, as you would like to call it colloquially. Yeah.
Thanks.
Okay, good. Then let's move on. We also can look at the gluon propagator in QCD. So we look at everything which is bilinear in the fields. So we look at the field strength squared, and the bilinear terms come from d mu a nu, d nu a mu. So those are the terms here. We have the gauge fixing term, is also bilinear in the fields, we do our simple substitution of partial derivatives with a momentum to get the inverse propagator in momentum space. And this is basically the expression, so we have p squared g mu nu, which we get from combinations of two gauge fields here. And from the gauge fixing term, we get a p mu p nu with 1 over lambda here. And we also get a p mu p nu from other combinations here from the product of the two field strengths. So this is the inverse propagator. We can make a check that the gluon propagator is then given by this expression delta mu nu here, which is plus I times the Kronecker delta AB, and minus g mu nu over p squared, and then plus 1 minus lambda p mu over p mu p nu over p to the fourth power here. And multiplying gamma with delta, you basically can convince yourself that you get back a Kronecker delta in color and also in Lorentz indices here. And this also shows you why it's nice to work, for instance, in Feynman gauge, because in Feynman gauge you have a trivial propagator. If you put lambda equal 1 here, then this last term here vanishes and you just have a g mu nu. So then also the gluon propagator is fairly simple. Yeah. And then last thing, we can look at interactions that we derive from the inaction part of the action. So this would be, for instance, for the quark gluon interaction, we have the psi bar a mu or a slash psi, and if we strip away all fields, and basically what remains is the generator of the SUN gauge symmetry and the gamma mu, which is hidden here in this A slash, and so this is then the vertex for the interaction, which is the same as in quantum electrodynamics, except for this additional generator of the color generator here. So as a general rule, basically you can replace all the d mu by the momenta, also for the 3 and 4 gluon interactions, but this is a bit tedious and the expressions are then a bit lengthier. But in this way you derive what you typically find in any textbook on quantum field theory or the standard model. In the appendix you derive the set of Feynman rules for the quark propagator, the gluon propagator, and then also for the ghost propagator. Ghost doesn't have any Lorentz structure, so it's just I over p squared here. And then you also derive the Feynman rules for the vertices, the one for the quark gluon interaction I've just explained to you, and then the ones for the 3 and 4 gluon interactions, they are a bit more lengthy. So you see then you have like in total 6 terms for the 3 gluon interactions, which account for all the combinations of gluons with Lorentz index mu, momentum p, nu, momentum q, and rho, momentum r. Those are the combinations. And you also have the 4 gluon vertex here, which then has products of 2 of these color generators, 2 products of 2 f's here, and then combinations of metric tensors. And again, the ghost gluon interaction is a bit simpler. So this is unfortunately just the momentum of the ghost coming in times an FABC. Yeah. So this is basically how you derive them and how you can understand them. Now, if you want to apply them in practice, then basically you just copy them from slides or from your favorite textbook and you apply them. Except when you start to do actual computations, especially when you want to do perturbation theory at higher orders, it's not a good idea, in particular, to take the gluon Feynman rules as you derive them, because suppose you have a diagram which has like 3, 4, 5, 6 of those gluon vertices, which can easily happen at higher loops, then you just do your counting here. That means 6 times 6 to the power 3, 6 to the power 4, 6 to the power 5. This is becoming large, And so then when you actually want to do actual calculations, it makes sense to do a little bit of additional work on your Feynman rules. For instance, those Feynman rules simplify drastically if you encounter them in diagrams where, for instance, you have the 3 gluon vertex, but then you have the own gluon momentum dotted into this line here. So if you have this vertex here, but then this vertex is dotted with a p mu again. So you can work out what that means if you dot a p mu into this vertex here and you apply energy momentum conservation, and you see that out of those 6 terms you only end up with 3, and things simplify further. So this is a practitioner's rule or advice that you should follow, otherwise you'll quickly kill whatever computer algebra system you're using. Yeah? Then what is also important in QCD to take a brief look at the color algebra. So I told you we have these SUN generators, TA in the fundamental representation. We can trace 2 of them, and by convention we always normalize them to 1. The trace we normalize to 1/2 times the Kronecker delta in the adjoint indices here. And we can take 3 of those fundamental generators, take the trace of a commutator, multiply with a 3rd one, trace this, and then we have the completely antisymmetric FABCs. So those are the generators in the adjoint representation. You can understand this also pictorially, these rules, by looking just at the color structure of a 3 gluon vertex here. So these are 3 gluons coupling together. And then in terms of the color, so A, B, C is the color of those gluons here, you can understand this rule as resolving this interaction of the 3 gluons here by 2 fermions, which run, where you have a fermion loop here and an antifermion loop, so they run here clockwise and counterclockwise, and you simply take the difference of them. Yeah? Then in terms of algebraic properties, there are also nice things between those color generators which go under the name of Fierz identities. So if you have 2 of those generators TA and TB, and we keep the color indices I1, J1, I2, J2, we keep them open, then we can understand this as being the color part of QQ bar annihilation into a gluon, and then the gluon again splitting into QQ bar part, just the color part of that. Yeah? So we have open color indices I1 and I2 here, and then this goes into a gluon, and A with the color charge A, and here we have the color charge B of the gluon. By the gluon propagator, it is connected with the Kronecker delta AB, and then we have this gluon splitting into a open indices I2 and J2. And by this Fierz identity, we can decompose this into 2 terms. So one term is basically the Kronecker delta of I1 with J2 and J1 with I2. And then we subtract a piece which is 1/n suppressed, n being the SUN of the gauge symmetry. This is then the Kronecker delta I1 J1 and the Kronecker delta I2 J2. And pictorially you can understand this as 2 terms, of which you have to take the difference. The one is where the color charge just runs through. So the color charge of this quark here just runs through and connects to that one of the outgoing here. And likewise on the lower row, the color charge just runs through. And you have to subtract the term with a 1/n, while you contract the 2 color charges of the initial quarks and the 2 color charges of the final quarks. Yeah. So in this way, you can actually break down all the color algebra to manipulating fermion lines in the fundamental representation. This sometimes helps in understanding certain features. For instance, what you see from this decomposition right away is that sometimes it makes sense to consider gauge theory computations, not just in QCD, with a fixed number of color SU3, but keep the n general considered as an SUN gauge symmetry. And then you can take the limit of large n. And then you would say, okay, if we look at this expression here, the limit of large n means that this term here is leading and this term is 1/n suppressed, and then things simplify and you end up with what is typically called a planar limit of a gauge theory. So this also sometimes simplifies. I mean, we can start to argue whether 3 in QCD is actually a large number and whether it makes sense to do computations in the limit of 1 over 3 being large. But as a mathematical concept, just looking at an SUN gauge theory with n with an expansion in n being a large number, this makes sense, and it also simplifies certain diagrams significantly. And then there are useful relations between these color constants. So when we have two quarks, two generators, fundamental generators, Ta, Ta, we take the product of them, then we come up with what is called a quadratic Casimir in a fundamental representation, Cf. For an SUN gauge theory, this is n squared minus 1 divided by 2n, and in QCD this is 4 over 3. And for gluons, we have the product of two adjoint generators, so with F ACD dotted into FBCD, so we contract this over C and D as matrices, and we have a quadratic Casimir in the adjoint representation Ca, and this is simply n, so in QCD this takes the number 3. So these are useful relations. So this is about the Feynman rules, and then we can go ahead and we can do perturbative computations. If we want to do any computations beyond the leading order level, then there is another layer of concepts which we have to add, because intrinsically we're interested in the quantum effects of the theory, and in order to understand the quantum effects of the theory, we have to familiarize ourselves with the concept of renormalization. So the physics picture here is the following. So I told you we have our Lagrangian, and it depends on parameters, but those parameters don't have a unique meaning. So we can think of this as we're interested in a computation of a generic quantity R. Can be a scattering cross-section or something like that, and it depends on a hard scale. And a hard scale I denote by Q, can also depend on masses, and a hard scale is maybe set by whatever the hard interaction, transverse momentum exchange between two incoming particles or something like that. And we want to do a perturbative study in the strong coupling alpha S, and we want to also look at radiative corrections. And basically that means we are resolving quantum fluctuations, small quantum fluctuations at a given resolution scale. And the length scale that we can resolve is inverse proportional to some scale at which we can probe the system, so 1 over mu. Yeah? And that means the quantity we are interested in depends then on the resolution length, or its inverse, the scale mu, at which we are probing the system. So basically tells you, just from these considerations, it tells you that whatever measurement you make, it depends on the resolution that you're looking at it. Yeah? So this is the important thing. And once we have realized this, then we can formalize this in a so-called renormalization group equation, which is fairly general for quantum field theories. So we have our quantity R. It depends on a hard scale. It depends also on masses. And for convenience, we can make dimensionless ratios. So we can make a ratio of the hard scale over our resolution scale, Q over mu. And we can also take all the quark masses in relation to the hard scale. So if this hard scale is really large, like a TeV at the LHC, and our quark masses is fairly small, and this already tells us that we can, for instance, stop the quark masses. And then we also have dependence on the strong coupling here. And then, since all of these quantities depend on the scale at which we resolve the theory, there is an evolution equation, or a renormalization group equation as it is called, which parameterizes as a differential equation the way our quantity R changes when we change the scale. So we first start with a partial derivative, d mu over mu squared. This is just telling us how R changes when we change the scale. But then we also have to take implicit changes into account, like how does our coupling change when we change the scale. So we also take the partial derivative with respect to the coupling, dd alpha s. And then we have to, of course, by the chain rule, we have to multiply this by some coefficient, which we call beta, which is basically the partial derivative of our strong coupling with respect to the scale. And then we also have to account for any changes of our quantity r with respect to the mass when the mass changes its scale. So this is then partial derivative with respect to the mass parameter, and then this is multiplying a gamma, which is the gamma times m is basically the partial derivative of the mass parameter with respect to the scale. So this is fairly general, just telling you or starting from the assumption that when we make measurements we just look at quantities at a given resolution scale, and then we write down how these quantities change in general, and then we can try to solve it. Yeah? But in order to do that, we first of all have to look a little bit at how do we actually do those computations, and that leads us to a few technicalities. So if we are now interested in resolving these quantum effects in a gauge theory, then we have to look at radiative corrections. So a simple example is here the Scalf energy in a scalar theory. So you have a scalar coming in and it splits up into two scalars, and then they annihilate again into one scalar, and that's it. So this is the simplest example, I think, of a quantum correction. And then we can, since we just have scalar propagators, we have, say, this scalar propagator here has momentum L, and this is L minus Q. And then since this is a virtual quantum effect, we need to integrate over all the loop momenta that can appear here. So we write down an expression like 1 over L squared times L minus Q squared, and then d for L squared. Since we are in 4 space-time dimensions, we need to integrate. And then this is giving us contribution to the quantum corrections of a scalar quantum fluctuation. Now you do your power counting, so you can see whether you can actually make sense out of this integral. So you have a 1 over L squared here, then you have an L squared in this propagator. So when the loop momentum L becomes large, since you integrate over all loop momenta, then you have a 1 over L to the 4 in the denominator, and you have your integration measure in 4 space-time dimensions. This is d for L. So you can easily see from power counting that this integral here has a logarithmic divergence. It means it diverges in the ultraviolet for large loop momenta, and you have to make sense of it. Yeah? Right. And the way to make sense of these ultraviolet divergences is intimately related to the concept of renormalization, and this is also what got Toft and Feldman 25 years ago the Nobel Prize in Physics. And on the website of the Nobel Prize Committee, they always give some. They try to explain the achievement of the Nobel laureates in simple words, so that also the public can address it. And the sentence or the headline they came up with to explain the achievement by Toft and Feldman in this way was "Goodbye to Infinities." So they came up with a consistent framework in order to cancel all ultraviolet divergences in gauge theories. So how does that work? So we have a even simpler example for an ultraviolet divergent loop integral. So if we take this in a Euclidean region, then we have a massless tadpole here. So this is just a massive scalar propagator contracting into itself. This is a d for L over 1 over L squared plus mq squared. It again diverges in the ultraviolet for large loop momenta. And then in order to make sense of such expressions mathematically, you have to regularize it, meaning you have to introduce some ultraviolet cutoff, which is very easy. So you just do your loop integral here, and then you integrate just up to loop momenta up to some cutoff lambda. This is what people did initially. Problem is that when you do this, you break in the gauge theory, you break Lorentz invariance, and then you have problems doing your calculations, maintaining gauge symmetry or proving in the end that you have not violated gauge symmetry. So this is a simple approach that works at a one loop level, and one can do this for pedagogical reasons. One can do computations with a cutoff, but in practical applications we don't do it. And then the next best thing people came up with was so-called Pauli-Villard regularization. This means you have a propagator 1 over L squared here, for instance, and you replace this propagator by a large fictitious unphysical mass. So you replace it by 1 over L squared minus M squared, and M squared is very large, but it's cutting off things in the ultraviolet. And then you can also do your computations. But it's very tedious because massive integrals are much more difficult than massless integrals. So this is also what people didn't like. Then there is, you can put things on a lattice. There will be more lectures on lattice QCD during the school here. What we do in perturbation theory is actually we do dimensional regularization because it keeps Lorentz and gauge symmetry manifest. And dimensional regularization is just we take these integrals here, which live in 4 space-time dimensions, and we do an analytic continuation, really in a mathematical sense, of this quantity here from 4 space-time dimensions to d space-time dimensions. So meaning we basically replace the integration measure in a loop integral, d4L by d capital DL, and d is now 4 minus 2 epsilon. And epsilon you can think of as a small number, yeah, but we have moved things away from 4 dimensions in the complex plane in dimensions. It also requires us to consider our Lorentz indices mu in d dimensions, so they don't run from 0 to 3, but they run from 0 to d. We have our Lorentz vectors now. We also continue them to d dimensions. And also our metric tensor, at least a trace of the metric tensor now gives us d, the dimensionality of space-time. And we also have changes in the Dirac algebra, because you know that when you do your anti-commutator of two gamma matrices, gamma mu, gamma nu, then in 4 dimensions you would end up with 2 times g mu nu, the metric tensor. But now if you have an expression where you take g mu, g nu, gamma mu, gamma nu, gamma nu, mu, and you contract 2 of them, then you don't get minus 2 again, minus 2 gamma mu, but you get 2 minus d as a prefactor here. So this is then also the analytic continuation of the Dirac algebra. But you could, in applying this, you basically have to think of this as simple analytic continuation like you do in functional analysis for simple functions. Now we just do it here for loop integrals. Yeah? Okay, then you are done with this.
Is there a way can we connect Pauli-Villard with dimensional regularization? For example, poles in the integral, dimensional regularization will have 1 by epsilon square, 1 by epsilon type of poles. In Pauli-Villard we will have log m square, log square m square. Can we relate?
So there are rules, especially at the one loop level. There are rules how you can translate poles in epsilon in dimensional organization to logarithms in Pauli-Villard. At higher orders, it becomes tedious because of nested singularities. Yeah, so there are ways how to connect singularities in dimensional organization to logarithms in the masses, but this is more researched in the context of infrared singularities. For Pauli-Villard, I'm not actually aware of anyone has worked it out beyond 1 loop.
For example, let's say we divide our integral into infrared part and the UV part. It's a UV part we know, infrared part we can relate somehow with that.
In the infrared part there are relations. So basically you can look at, you can understand how to relate simple poles and dimensional regularization to logarithms in a mass which regulates in infrared singularities. This is known and this is being applied also. Okay. Now,
There's one question.
sorry.
How can you say like if cut off schemes gauge impedance is lost and Dimrack it's maintained? I didn't understand that.
This is another problem of the Pauli-Villard scheme. And in the cutoff scheme, so basically you have to see when you do your, you have to go back basically to the Lagrangian, the QCD Lagrangian, and see how's the gauge transformation acting on those fields here. And it is involving basically the entire quantum field, and you don't restrict it to any region in parameter space and in space-time. Yeah? So that means if you now do your loop integrations and you suddenly say, okay, I have here say a gauge field running around, but I cut off parts of space-time, then it's not clear how you maintain gauge invariance in the end. Yeah?
But at the end we can take lambda to infinity, right? So
in the end we would take lambda to infinity, yeah, of course, and then
so we are not actually restricting that.
And it basically the powers of lambda, so or logarithms of lambda, so those would be log singularities that come in there. Those log singularities basically give us a power counting for the ultraviolet divergences. And then we have to absorb them.
For vector gauge theories is fine, but for chiral gauge theories, I guess one has to put in infinite number of Pauli-Villard regulators.
Sorry, for?
Chiral gauge theories, like standard model.
Um,
So there, how one fixes the masses and all, is it known?
I'm not aware of this being really applied beyond one loop in simple examples. So Pauli-Villard was the way people started doing computations in the early days of quantum field theories, and once dimensional regularization was realized as being much more versatile by the end of the 1960s, I'm not aware of any practical computation being pushed in this direction with Pauli-Villard anymore. I mean, the other part is basically that once you really have a mass in your integral and you go to higher loops, say 2-loop, 3-loop level, then it becomes unfeasible.
Thanks.
Okay. So now we have regularized our loop integrals, and we want to continue with the task of relating or identifying the resolution dependence of our parameters in the Lagrangian. And what we have to do is basically, in a nutshell, we have to compute vertex corrections and self-energy corrections. So self-energy corrections are all the types of quantum corrections we can have when we have a quark, a gluon propagator, or a ghost propagator with loops inside. Or we have the vertex corrections, which are typically the gluon going into QQ bar pair, or the 3-gluon, 4-gluon interactions. And we compute them. So the 3-gluon vertex, for instance, is the coupling of the 3-gluon fields here with a strong coupling, power of the strong coupling before, and the quark-gluon vertex is the gluon field psi bar psi, and power of the strong coupling here. And then we do our computations to a certain order in perturbation theory. Say we do this at one loop, meaning we put in here all the particles which can appear in one loop quantum correction. And we calculate these vertices, and there will be infinities, ultraviolet divergences. And then we can make a redefinition of our bare quantities, which we calculate with the Feynman rules, and we simply split them into products with so-called renormalization factors, Z factors, where we say, okay, we split our ultraviolet divergences in Z factors, say Z1 factor here for the 3 gluon vertex, and this multiplies a renormalized vertex. No? Likewise, we do this for the quark gluon vertex here. We multiply a Z1 for the fermion gluon-fermion interaction with a renormalized quark-quark gluon vertex, and for the fields, we take renormalization constants Z2 and Z3. For each field, for conventional reasons, we take the square root of this. So for the quark field, we take the square root of Z2. For the gluon field, we take the square root of what we call Z3. And then we also have the coupling in the game here. So we say we can rephrase our bare coupling as a renormalized coupling times a Z factor. And likewise, we do this for the masses. This we can always write down. The point is, how can we make sense out of it? And we can make sense out of it when we consider this as a procedure of multiplicative renormalization. So first thing to notice is that we have, when we deal with the gauge theory, then we can of course introduce all these Z factors here for all the self-energy corrections and the vertices that we compute, but they are not all independent from each other, so there's some residual relations between them. For instance, when we have the 3 gluon interaction, Z1 here, this is 3 gluon fields and 1 coupling constant here. That means the Z1 constant here can be related or is given by the factor which we put to the coupling constant and the Z3 constant which we put to each gluon field. So this is one relation which we have. And likewise the quark-quark gluon vertex here is 1 gluon field, 2 quark fields and a coupling constant. So it is related to the ZG factor times 1 factor Z3 square root for the gluon field and a factor Z2 for 2 quark fields. And these type of relations, you can write them in different combinations, and they go under the name of Snow-Taylor or Ward identities, and they are a consequence of gauge invariance of QCD, meaning you can do many computations for all of these quantities in your gauge theory on QCD, and in the end, these factors which you've introduced, they must be related in precisely this way. And if you don't find such relation, it means typically that you have a mistake in your computation. Then, once we have done such a computation, say we have done the quark self-energy here, and we have computed our bare result and extracted our ultraviolet divergences, then we can express our bare Lagrangian with a bare field in terms of a renormalized Lagrangian and a so-called counter term, where we basically split, or the counter term Lagrangian is all parameters multiplied with a factor z times -1. And then in this way we have a formal way of separating all ultraviolet divergences which we ever encounter in our theory. And the nice thing about a gauge theory, a renormalizable gauge theory, is that we can do this at every order in perturbation theory with just a finite set of factors. So this distinguishes renormalizable from non-renormalizable theories that, say in QCD, we have this finite set of fields and that's it, and we don't need anything more at each order in perturbation theory. Right. So, in practice, what do you need to do? Let's look at the strong coupling. And let's look at the one-loop quantum corrections that we need to account for. So we have a quark and quark-quark gluon vertex. So there can be a gluon exchange here in this triangle. And this is like a one-loop correction that we have for the coupling constant. There can also be the gluon which couples to the quark that can have a virtual quark pair here in the loop. And those corrections we can compute. And they tell us how the coupling constant changes as we change the resolution scale mu. Huh? And this is basically what you also have in quantum electrodynamics. So if you know quantum electrodynamics and you know how the charge changes as you change the resolution scale, then those quantum corrections are basically describing the screening of a charge. Yeah, but in QCD we have also 3 gluon interactions. So we have the triple gluon vertex here that we have to account for, and we have to also account for gluon self interaction in the gluon propagator here. So these are new additional diagrams, and if we compute them, they are responsible for anti-screening of the color charge. And computing those diagrams, so this whole set of diagrams, we can then go back and make sense to the initial ansatz that we had when we were discussing generalities of perturbation theory. And we said, okay, we look at a specific quantity R, we look at its direct changes with the resolution scale mu, but we also look at how the coupling, how it changes with the coupling, and then we also have to account for how the coupling changes with the resolution scale mu. So now we have computed, or we look at those graphs, and looking at these graphs precisely tells us how the coupling changes with the resolution scale, and this is basically what you have to compute when you want to compute the beta function of QCD. And doing these graphs here basically gives you the first term in the perturbative expansion of the beta function here. Interesting thing is, what people discovered is that the beta function has a negative sign here. So basically that means if you look at this relation and you go with the normal, with the standard coefficient for the beta function at one loop, which is 11 over 3 times Ca minus 2 over 3 times Nf. So Nf dependence is the number of fermion flavors, which comes from this graph here, and then 11 over 3 times Ca comes from these graphs here, from these graphs in particular, and for 6 flavors, so if you include up, down, strange, charm, bottom and top at high scales, then this is, for instance, giving you 7 over 4 pi. That means the negative sign of the beta function means that as you go to higher and higher energies, the coupling becomes smaller and smaller. It means quarks and gluons are interacting freely. And this is goes under the name of asymptotic freedom, discovery of which got these gentlemen the Nobel Prize around 20 years ago. And if you look at this renormalization group equation now for the strong coupling alone, you can solve it. And the negative sign of the beta function basically means as a function of a hard scale Q, starting off say at 1 GeV and going up all the way to 10 to the 4, 10 to the 5 GeV. You see that the coupling becomes smaller and smaller and smaller, and at asymptotically large scales it vanishes, whereas at small scales, so at scales of the order of the proton mass, it is very large, and eventually it diverges as you go to 0 scales. So that's the explanation for quarks and gluons being bound in protons, so that you cannot see them as they don't appear as asymptotic states in nature. They just appear as asymptotically free states here. And state of the art in this computation here is that the beta function has now been computed to 5 loop order. So this is 1 loop, 2 loop, 3 loop, 4 loop, and then the next term is 5 loop. So we know this rather precisely. And in this plot, I show you the successive perturbative expansion. So the dotted line here is if you look at the change of the coupling constant at the 1 loop level, then you have the black line is the 2 loop level, 3 loop level, 4 loop level. So you see also that if you push perturbation theory to higher and higher orders, the corrections become successively smaller. and we see quite good perturbative convergence here. Yeah. Okay, now I've solved the differential equation here, first order differential equation, and I've given you a plot, and now even with undergraduate knowledge in physics and mathematics, you should tell me, look, you cannot solve a first order differential equation without telling me what's the boundary condition. So we need at least one boundary condition, and it basically brings us to the question, how do we determine the strong coupling? What's the boundary condition in order for us to make this plot here? Well, in this plot I've already given you the boundary condition. So in solving this, I've chosen a value of the strong coupling at the value of the Z boson to be 0.115. Now question is, how do I know this? And in order to understand how to get the boundary condition, we have to go back to what I said in the beginning. The coupling is just a parameter of the Lagrangian. It doesn't have any unique physical interpretation. And if I compute, especially if I compute these quantities here, like the beta function, they depend on the way how I do the renormalization. So there is a renormalization scheme dependence. And I cannot just measure the strong coupling. So I cannot go to the Large Hadron Collider and take a set of data and extract a strong coupling. But what I have to do is I have to look for suitable observables which depend on the strong coupling. And then I have to take data and I have to look at how does this observable change when I change, for instance, the scale at which I probe or which I take a certain cross-section, and how does it change and how do I relate those changes then to changes in the strong coupling. So you can think of this as, for example, being a measurement at the Large Hadron Collider of 2 jets in the final state versus 3 jets in the final state. So 2 jets would be 2 partons, quarks or gluons, and 3 jets would be 3 final state partons. So each additional parton in the final state has 1 power in the coupling, and by comparing the ratio at different say transverse energies of the jet or something like that, this gives us a way of extracting then the strong coupling at that transverse momentum scale, for example. So this would be one suitable observable that we can look at and do our measurement of the strong coupling, or extract it by comparing data to theory. This is basically the point I would want to make here. And this has been done already many years ago, so more than 30 years ago. Stefano Catani and Siegfried Bethge got together and they compiled all the then known measurements, useful measurements that had been done with dependence on the strong coupling. And so this was Z boson event shapes, the Z boson decay width. These were scattering cross sections at proton-antiproton colliders with bottom quarks in the final state. Also E plus E minus annihilation, deep inelastic scattering, things like that. And they extracted a list of values of alpha S, and since then this boundary condition which you need to solve the beta function has typically been taken as quoting the value of the strong coupling at the value of the Z boson mass. And back then it was extracted as 0.117 with some uncertainty. And if you study this table carefully in detail, then you'll also see that the values of alpha S that were reported at that time were not really compatible, because there were some measurements that reported a high value of alpha S, some measurements that reported a low value of alpha S, and then people somehow said, okay, let's close our eyes, we just average. Yeah? But now we are 30 years further, so alpha S in 2024, this is the last update of the PDG, of the particle data group from last year, gives you the alpha S determination from a much larger class of quantities now, so from tau decays, from quarkonium bound states, basically from parton distribution fitch, which is mainly deep inelastic scattering, from E plus E minus jet rates and event shapes, from hadron colliders, jets, top quark productions, from electroweak precision fits. And you see that, for instance, alpha S determinations from E plus E minus still somewhat give you a larger value of alpha S. Alpha S determinations from deep elastic scattering still give you a smaller value of alpha S. So basically on the side of data extraction or data to theory comparison, the situation hasn't changed much. We have improved our theory predictions. So back then, next to leading order QCD theory predictions were available. Now we have moved to next to leading order QCD theory predictions. But we haven't really gotten any further in understanding this. There is some potential for alpha S extractions at future colliders, like a future circular collider with electron-positrons colliding. People claim that you can extract alpha S at a percent level precision. Well, what you should keep in mind is basically that whenever somebody tells you or shows you a table like this, you should look at a fine print and go back and ask yourself, okay, what is the data that's been used and what is the theory that has been used to compare to those data? Because many of these discrepancies, even when people claim that they are analyzing the same data, like alpha S values here and here, or here and here and here, many of these discrepancies, they can be localized in having different assumptions about the underlying theory there. Yeah. I think today alpha S value is, then if you average, if you basically close your eyes and disregard all these discrepancies, then you come up with a value of 0.118 roughly, with a very small uncertainty. But in order to really appreciate all these measurements and also to distinguish them, you should look a little bit at the fine print. Okay, that was about the strong coupling. Renormalization, let's also speak quickly about quark mass renormalization. So when we...
excuse me, I have a question. So when you show this combination of alpha S, the covariance uncertainty of E plus E minus collider versus hadron collider, etc., are quite different. So how those are taken into account while making this combination?
That's a good question. So basically, I think it has been recognized when people became more critical of this, it has been recognized that in some extent this is comparing not like with like, you know. And even within, say, even within a given set of determinations, like alpha S determinations predominantly from deep elastic scattering data, like here, you have a large spread, and so in order to appreciate and understand this, you really have to go into the detail of each analysis and see, okay, what have been the assumptions, theory assumptions, what's been the data, and if we then say, okay, data is largely similar, then what have been the theory assumptions for each of those extractions, and how they have an impact on the value of alpha S that you extract at a given scale. So this is, I think, the first question to ask. And then when you look at, when you answer this, then you basically would say, okay, you cannot really average things like that because there is different underlying theory assumptions, and if we're strictly speaking, then one is wrong and one is right, yeah? Because in the end, we have to decide, and this is something that I think the community is not really is evading, you know. I mean, in principle, you have to say some of these determinations will simply not be correct. I think for tau decays, this has now been clarified. There have also been large discrepancies in the past, but this has now been clarified. And there is also agreement in the community. In other cases, like here, E plus E minus, there is an ongoing discussion, yeah? Basically then relates to the fact that, for instance, when you do analysis of lab data for E plus E minus, how do you account for uncertainties in Monte Carlo modeling, in power corrections, things like that. So there is a whole list of things that you have to do there.
Thank you.
So there are regular Alpha S workshops, and if you go to or join one of these Alpha S workshops, then people are heavily debating or fiercely debating and defending their determinations. Was there another question?
There is. I have one, but maybe you continue. You continue.
So when you calculate alpha is from QQ bar bound states, then one needs the string tension as an input. So is this taken from lattice, or how much uncertainty of that affects this measurement?
There are alpha S determinations using QQ bar bound states from using the string tension from the lattice. There are other determinations using some rules, and they also give you a large spread in the alpha S values. Yeah? So this is also one of the discrepancies that we have using different methodology there. So no, I mean this is the PDG summary. Not all of the alpha S determinations they end up in the summary plot. This is just giving you a coarse impression there, but I think it's fair to say that any of these categories with which the particle data group came up with, when you look closely into it, you will always find determinations where there are some discrepancies, and using different theory methodology, and this has to be addressed. I mean, of course, there is the lattice point down here. So this is the value from the this is very precise value that has been derived with lattice QCD. So if you talk to people from working in lattice, then they will ask you, why don't you take alpha S from the lattice as a fixed number and fit everything else? The practitioner's point of view is, I can do this, I can fit LHC data taking this, but then I will get a horrible chi-squared. So there is simply theory framework and the alpha S values, there is some tension there. And so this is why we typically like to fit LHC data or collider data also having alpha S as a free parameter, because it basically tells us, it guides us and shows us theory tensions there.
Is it because the Monte Carlo modeling of the experiments, they have uncertainties, or that is you're taking it in the alpha?
It's more than that. It's also basically doing the theory framework beyond the leading power factorization that we have. Yeah? So I want to talk a little bit about factorization tomorrow and on Wednesday. But basically this whole factorization ansatz that relies on leading power. And then the question is, what comes beyond this? Corrections which we don't have in perturbation theory, which are not really well modeled in Monte Carlos, and then this is giving you a bias depending on the kinematics in that you're probing.
About the same precision determination from the lattice, typically most harmonic measurements one get to see that experiments supersede lattice estimates by like order of magnitude. I mean in terms of the error, while in this case lattice is dominating any other errors. Do we have an understanding on why that is the case? If we have an understanding, then we can explain why this is actually leading to large chi-square in using that for experimental fits, right? Probably.
So the lattice number comes with this very small uncertainty, and this is, I mean, lattice simulations, they sit at small scales. Then you have to evolve this on a lattice. You have to do at some point your matching to perturbation theory. Then you have to evolve in perturbation theory to come up with a value of alpha S at a perturbative scale like the Z-boson mass. And so you can question all the systematics on the lattice side, including the matching to perturbation theory and so on and so forth. This is one thing. And then you can say, okay, I take this at face value with a very small uncertainty, and now I start doing my fits of collider data. And then I can make a fit, I can fix alpha S, and I let all other parameters freely, and I see my chi-squared parabola, and I will have an optimum, but then with that alpha S value I'll be way off. This is what I'll be seeing. Yeah? And then I look at the theory that I have to fit my collider data, and then if there are no other free parameters other than alpha S to let it float, yeah, to some optimal value, then what can I do, yeah? And this is the outcome in a nutshell. Okay, right. So let's.
Sorry, we have 5 more minutes.
Yeah, I was just going to say I have to speed up a little bit. So I just wanted to say we also can do quark mass renormalization. So just for those of you interested, this is really the calculation of a heavy quark with a gluon exchange here. And if I run through the whole computation, doing my bare 2-point function, then this is the expression here. I get alpha s in d dimensions. I get alpha s over 4 pi squared. I get mu squared over mq squared to the power epsilon. And then I get 2 terms. I get a term proportional to p slash minus mq. This is, and then I have a ultraviolet divergence 1 over epsilon minus times minus cf. And this is the part which goes into the wave function renormalization. So this would go to z2 or z psi as I've called it here. And then I have another divergence, ultraviolet divergence, which is proportional to the heavy quark mass, and this goes into the heavy quark mass renormalization. And then I can define my renormalized heavy quark propagator by adding the counter term here, which basically absorbs the ultraviolet divergence. And then I have to make a choice, in particular for the heavy quarks I have to make a choice, how do I do the subtraction? And then one way I can do the subtraction of my ultraviolet divergences, I can go to what is called the pole mass scheme. It basically means I have here my heavy quark propagator with all the divergences here, and then I can say, okay, what I would like to have as a renormalized quark mass, I would like to have a pole mass, meaning that when I take the momentum on shell, I take the momentum p slash to be mq, then I would like to have the mass to be the pole of the propagator. This is done in quantum electrodynamics, for example, and this is sensible when you have a particle which also is in an asymptotic state, like an electron, which is a stable particle. Now, when this is done in QCD, this is strictly speaking not correct because quarks are not asymptotic states, they are only bound in hadrons. Nevertheless, we like to do this pole mass renormalization scheme because it's conceptually simple, and we can easily implement it in computations. Alternatively, what I can do is for the heavy quark mass, I can do something like the MS bar scheme. And then I just subtract the pole part here that I have on the previous slide, and then my mass becomes also scale dependent and it starts to run. And then I have an evolution equation also for the heavy quark mass, so then the value of the heavy quark mass also depends on the scale at which I probe it. And this plot here is for the top quark mass, for instance. So this is the top quark mass is 163 GeV, and then it runs down to smaller energies at 1 loop, 2 loop, 3 loop, 4 loop level with this renormalization group, and now some anomalous dimension which governs the running of the heavy quark mass. So it's similar to what we just discussed for the strong coupling for the beta function. You have the mass anomalous dimension for the heavy quark, which then determines the running of the heavy quark mass. And of course, being equivalent schemes, you can go with a finite scheme transformation. You can take any pole mass and you can convert it into running mass at a given order in perturbation theory, and you can go back and forth. Yeah? And some schemes are more advantageous than others, especially if you look at charm quark physics. The charm has a very small mass and sits at low scales, so the pole mass for the charm has poor perturbative convergence. So this is typically why charm physics is done with a running mass, whereas for top quark physics at the LHC, you have the pole mass scheme and the running mass scheme alike. Yeah? I think in view of time, I skipped the comments on decoupling. I was just going to say how we're going to treat theories with different numbers of heavy flavors, how we decouple them, and how this decoupling then manifests itself as we go across flavor thresholds. The slides should be on Indico. You can look at them and you can come back with questions on that tomorrow. I would like to summarize for today. Just gave you a basic introduction into QCD and try to highlight a few things that we have to pay attention to when we do renormalization of QCD, subtraction of ultraviolet singularities, definition of the scheme, and I have pointed out to you that the parameters like alpha S and the quark masses are not observables, but we have to determine them from comparing to actual calculations. So that's it. Thank you very much.